We have made it to our first non-linear data structure, trees. Going to be fun. We're going to cover trees, binary trees, their implementation. We're going to cover a variety of traversals of these trees, breadth first traversal, depth first traversals, and we're also going to be introducing the idea of binary search trees. A lot to cover. So we're going to start out with just some tree terminology. What are trees? Just another abstract data type. It's a data structure made of both nodes and pointers, very similar to a linked list in that regard. The difference, however, is in their organization. Whereas a linked list is a linear structure, right? We have a predecessor-successor relationship, which is now well established. A tree represents this hierarchical relationship between the nodes. I say here this ancestral relationship, similar to what you would see in a depiction of a famous family tree, right? Where you have a parent or there's some great grandparent of the family, their children and their children's children, and so on. A node in a tree can have several successors, which we call the children of that given node. And a node's predecessor you can think of as its parent. So some basic tree terminology. The top node in the tree is called the root of the tree, which is a bit different, right? A root of a traditional tree outside is going to be in the ground. Here, the top node of that family tree is going to be that root, where that tree is rooted. And the root is a root because there is no parent above that root. It is the final ancestor along that tree. Every node in the tree can have children nodes, and every child node in turn can be a parent to its own children nodes. Nodes that have no children are called leaf nodes, or you would just call them, the plural, leaves. So a leaf node is a node with no children. Any node that is not a root or is not a leaf node is simply an interior node. Another important definition is the height of a tree. The height of a tree is defined as the length of the longest path from the root to a leaf. There might be many paths from a root to a leaf, but the longest one is the height of the tree. And a tree with only one node, which would be the root, has a height of 0. So that's a lot of terminology. We're going to have more, but let's first just look at a picture of a tree. Here's a tree. Pause the video. Ask yourself, what is the root of that tree? I hope you can see the root is 2, right? 2 is the root. Which nodes are the leaf nodes? And the answer is 2, 5, 11, and 4. Those are leaf nodes. Why are they called leaf nodes? Because they have no children. And the other nodes, which are going to be the 7, the 5, the 6, and the 9, those are not leaf nodes. They're clearly not the root. Those are just your basic interior nodes. Let's look at this idea of a subtree. A subtree of a given tree, T, is a tree consisting of a node within that subtree and all of its children, all of its descendants. So here's some tree right here, rooted at 17. Well, here is a subtree. So a subtree of a tree is a tree consisting of a node and all of its children. So here, if we look at this node 9 and all of its children, which are just 6 and 5, this right here is a subtree. 15, 8, and 10 is another subtree. Let's head over to the tablet and let's look at a few more. With the blue pen. So here, all of this would be one subtree, right? A subtree of a given tree. So here is a tree. What is a subtree of that tree? Any node and all of its descendants. So let's say I pick node 9. Well, node 9 and all of its children. Well, node 9 does not have a child over here, right? There is no child there, but there is a child to the left, right? We have this 4. So node 9 and all of its descendants, that is a particular subtree rooted at node 9. Let me give another example. How about node 5? Pick node 5 as the root of some given subtree. And so what is the subtree that is rooted at 5? It is going to be 5 and all of the children of 5 and all of their children and so on. That is a subtree. Well, what about the subtree that's rooted at 11? That would be node 11 and all of its children. And there are no children of 11, so that is a subtree. So one more time, what is a subtree? It's a tree that consists of a node as well as all of its children. So here, you could say this is a subtree rooted at 6. Here's a subtree rooted at 7. Here's a subtree rooted at 2, and all of its descendants are there because there are no descendants from 2. Here's a subtree rooted at 4. If I were to ask you, is that a subtree? The answer would be no, because it does not include all of the children of 9. So that would not be a subtree. Or if I were to say, is this a subtree? You'd say no, because you have to look at the top of that subtree, which is 6, and therefore you must include all of the children of 6 would be all of those nodes right there. That would be a given subtree. That's another term, this idea of what is a subtree. Binary trees. So a tree in which every node can have a maximum of 2 children is called a binary tree. So on the previous examples, this picture I showed you here, every node has only 2 children. On this picture as well, every node has at most only 2 children. But in a regular tree, nodes can have 100 children, thousands of children, right? But a binary tree is a tree in which each node has a maximum of 2 children. Each node can have no child, each node can have 1 child, or each node can have 2 children. And a child can only have 1 parent. How do we know which is the left child of a node, which is the right child of a node? We simply use pointers. So here's examples of 2 very basic binary trees. Here's a tree with a root and 2 children. Here's another tree with a root, 2 children, and this right child has a left child, and this left child here has 2 children. But it's a binary tree. Why? Because no child or no node has more than 2 children, and no node has multiple parents. Here's examples of 2 trees that are not binary trees. Clearly, this one is not, because here we have an example where a node has 3 children. That's not a binary tree. And why is this not a binary tree? You might be looking, well, I see this has only 2 kids, this has only 2 kids, this has only 2 kids, each of these has no kids. It seems like it's fine, right? Except right here, what's the problem? Here, this node has 2 parents, and therefore that is not a binary tree. Some more terminologies. What is a full binary tree? A full binary tree is a tree where every node, other than the leaf nodes, has 2 children. Every node, other than the leaf node, has 2 children. So if you look at this tree, if we ask, is this a full binary tree? Well, notice we look at the leaf nodes, G, H, E, and C, and we see that, okay, fine, those are the leaf nodes. What are the other nodes? A, B, and D. So we ask ourselves, do those non-leaf nodes, do all of them have exactly two children? A has 2 children, B has 2 children, and D has 2 child nodes. Therefore, all of the non-leaf nodes, each one of them has 2 children, and therefore we can say this is in fact a full binary tree. Another similar sounding from full to complete, another term, complete binary tree. What is a complete binary tree? I will tell you, full binary tree has less of a use. It's an important term to understand. There's some use cases, but we will be using complete binary tree often, and the meaning that you grab from a complete binary tree. It's going to come up later, but we're going to use it often. What is a complete binary tree? It's a tree where every single level, with one exception, but every single level is completely filled with the exception of possibly the last level. If the last level of the tree is not filled, all of the nodes must be as far left as possible. Now, what we're depicting here is a completely complete tree, meaning every level is filled. And what I mean for clarity is here we have level 0, right? And I'm going to call this a height of 1, but level 0, at this level, let me actually come over here to the tab. Let me pause. All right, through the magic of pause, let's go. We now have here the tab open, and we have this exact tree that we want to look at. This is a complete tree. Let me actually open up even a different complete tree. I'm going to go back to the home here. I'm going to pull up the exact tree that we have open right here, which is this one. These are both complete trees, but look at this tree right here. Every single level is completely filled. So here's this topmost level. There's only, of course, one node at that top level. And here's this next level. Of course, the next level should have 2 nodes. This next level, of course, should have 4 nodes. This next level, if it's completely filled, should have 8 nodes. If there was another level, and if it were completely filled, it should have 16 nodes, right? Because it's just doubling. If every node has two children, the number of nodes at each level will simply double. So here, the definition of complete binary tree is every level except possibly the last level must be completely filled. So here, notice that we have 4 levels. So ignore the last level, which is this level right here. Ignore that for the moment. Look above. Do we have a situation where each of these top 3 levels are completely filled? And the answer is yes. You might be thinking, okay, well, what would be a scenario where that's not the case? Well, let's look at one. I'm just going to draw one. Let me move this one to the side briefly. If I'm just going to draw this tree right here, here's a tree, node, another 2 nodes, and let's say I did this. And each of these had 2 kids, right? Here, we can see this uppermost level is completely filled, right? The next level is completely filled. We can see that. But this third level right here is not filled. It's not completely filled because we're missing that node, right? And so the definition of a complete binary tree is, one more time, let me erase this. There we go. Oh, come on, erase. Erase all of this, cool. And let me drag this over. The definition of a complete binary tree is where every single level is completely filled, with one exception. The last level does not have to be completely filled. But, here's the but, if the last level is not completely filled, any nodes that are missing on the last level, they must be missing from the right side. So for clarity, hypothetically, if we had this last level, and pretend that these 2 nodes weren't even here, okay, pretend that node 6 had no children, that would still be a complete binary tree because the only level that's missing nodes is the last level, and any missing nodes are on the right side, or the way the slide worded it, it said that all of the nodes are as far left as possible. See, all of these nodes here that are on the last level, they're all aligned to the left, right? The space that we find, the nodes that are missing, are these nodes on the right side. So therefore, that would still count as a complete binary tree. But what if we were missing this node right here? If that node was missing, everything else was there, but that node's missing. That would not be a complete binary tree because there's a missing node on the last level, and that missing node is not on the right side. So I hope that's clear. This particular depiction is as complete of a complete binary tree as you can possibly get because all levels are 100% filled. So some more binary tree goodies. Here we have the root is level 0. Then we have level 1 is the next level, level 2, and level 3. What is the height of this tree right here? Pause the video. Think back. Hopefully you're paying attention, taking notes. What is the height of that tree? And a hint will be, what is the height of a tree with only one node, where that one node is the root? Think of the answer that we gave to that one, and then ask yourself, what is the height of this tree? So the height of a tree with only one node is a height of 0. So the height of this tree is going to have a height of 3. Because we have here the height of this one root node would be 0, and the height of a tree is defined as the longest path from a root to a leaf. So here we have from a root to this leaf is a height of 1, but now we look down from this root all the way down to the longest leaf, 0, 1, 2, 3. This tree has a height of 3. Again, the root is at level 0. The level of any other node in this tree is 1 more than the level of its parent. How do we calculate the total number of nodes in a complete binary tree? Think about that. The total number of nodes in a complete binary tree. I want to come back over here to the tablet. Let me hit home. Let's get a new whiteboard. And let's look at this and calculate. How can we come up with the total number of nodes in a complete tree? Let's think about that. What if we said the height of a given tree is 3? And we want to draw out that tree and think of how many nodes. Well, if the height is 3, there's going to be one node here, right? This is going to be level 0. This is level 0. Then we have level 1, level 2, level 3. I said a height of 3. Well, the next level, there's going to be 2 nodes. The next level, there's going to be 4 nodes. And this last level, there's going to be 8 nodes, right? So now you just add all of that up and see what it comes to. Try to add all these nodes up right here. We get 8 plus 4, 12, plus 2, 14, plus 1 is 15. So when the height is 3, we can get 15 nodes. When the height is 4, you're going to get how many nodes? Well, it's going to be these 15 plus now 16 more right there, right? There's going to be 16 more at that next level. So that's going to be 31. Okay. What about when the height is 5? If the height is 5, how many nodes will be in that tree? Well, it's going to be the 31 plus now the 32 nodes right here. That's going to be 31 plus 32. That's going to be 63 nodes. Can we develop an equation to come up with the total number of nodes in a complete tree? And the answer is absolutely, we can. This is your equation. It's 2 to the height plus 1 minus 1. So 2 raised to the height plus 1 minus 1. Let me write that down. 2 to the height plus 1 minus 1. So let's think about that here. If the height is 4, 2 raised to the 5th power, what is 2 to the 5? That's going to be 32. Minus 1 is 31, and that is exactly what we had just come up with. That's how you can calculate the total number of nodes in a complete tree. You can also calculate the height of a tree, approximate it using this equation. If you have 15 nodes, you can say, hey, well, that height might be 3, but that's assuming that is going to be a complete tree. Implementation of a binary tree uses linking to the left and the right in a very similar way to a linked list. We have a next. Well, now think of it, you have 2 nexts. You have a left and you have a right, similar to linked list. And so here we have our class, int BST node. We have a single data value, and then we have a left and a right. In the same way that we had a next of our LL node class, here we have an int BST node class. It has a left, it has a right pointer that's simply going to point to the left and the right child. What comes next is tree traversals, specifically depth first traversals and then a breadth first traversal. We need a way of zipping through our trees because we need to be able to search through our trees, find values in the trees, modify values. So we need to search our tree and traverse our tree. And you might think, well, why would this be challenging? For a linked list, we just go from beginning to end, right? It's pretty straightforward. Start at the head, traverse with a while loop all the way until the end. But we can't really do that for binary trees. Why? Because there's no such linear ordering of the nodes of a tree. It turns out there's actually going to be 3 such orderings that are called depth first traversals of our tree. And there's another ordering called a breadth first traversal. So there's really going to be 4 different ways that we can go about traversing our tree, and we're going to cover all of them. But we're going to start with what is called the depth first traversals. And there are 3 such traversals: pre-order, in order, and post order. And we're going to go over all 3 of them. But first, prior to going into the details of those traversals, we just want to understand in general, what is this idea of a depth first traversal? Given this particular tree, and notice it's not a binary tree, right? It's a good little question here because we have 3 children of this node H. But given this particular tree, a depth first traversal will explore a path all the way down to a leaf. And then it's going to have a dead end. And once it gets that dead end, it's going to then finally backtrack and try to explore a different path. So the idea of a depth first traversal is you go as deep down a path as possible until you get to a dead end. And once you get to a dead end, then and only then do you backtrack and try to go a different direction. So here, using this particular tree and using one of those particular traversals, we're going to see that we're going to search A, then B, then D. And then the search is after it's going to backtrack, after doing A, then B, then D, it's going to search, come back to B, and then it's going to try E afterwards. Nodes are explored in that particular order, but the takeaway here is that we're going to actually end up visiting N before we visit J, just for example, meaning we've gone all the way down a path before we even explore the right side of A, and therefore N is seen before J. And that's just in general. Now let's look at each of these three different traversals or depth first traversals of a binary tree. As mentioned, it turns out there's three such traversals: pre-order, in-order, and post-order. And the names of these traversals are chosen according to the step at which the root is visited. With pre-order, the root is visited between its left and right subtrees. With in-order traversal, the root is visited, so I said between. With pre-order, the root is visited before the left and right subtrees for the word pre. For in-order traversals, the root is visited between those two subtrees. And for post-order traversal, the root is visited after visiting both subtrees. That's a lot. We're going to go over detailed examples. It's going to be super clear. So here is our pre-order traversal. The root is going to be visited before the left and right subtrees. And when we say visit, we really mean print. When we visit a node, we're going to print that node, and then we're going to recurse in different directions. Here's the code. Let's just pause for a moment and see if we can fully understand this code. Public void is a void method, pre-order. We're given access to a particular node. Now, at the beginning of the traversal, we're going to be given access to the root, right? Because you need the root of the tree, we're trying to traverse it. So we're given access to the root. Now, I don't call this root here. I choose to call it some other variable name, P, on this example, because when we recurse, as you see recursion is happening, it's no longer going to be the root. It'll be the root of some given subtree, but it's not the root. So I don't want to call it root, I call it P. Now, at the very beginning, here we say if P is not equal to null, what does that really mean? That means if we have a tree, as long as the root is not null, so we have a tree at that particular node, what do? We print it. Then we go left, and then we go right. So let's make sense of this on an example. Here we have three nodes, A, B, and C, and we want to apply this code to this particular tree. So let's move over here to the tablet. We have the code and we have the tree. So let's look at what's going on. When we first come to this particular problem, we have here, I'm gonna grab the blue, and we have this here is our P, right? P up here is currently pointing to the root of the tree. Now, what does the code say? The code says if P is not null, do what? It says print the value that P is pointing to. So we're going to print the A. So here's our output. We're going to print A. And then what happens? We have this particular line of code. It says call this exact method recursively and send to that method P left. What is P left? Well, if P right here is pointing over to A, P left is what is left of A, which is going to be the B. So we're going to recursively call this method, and when we call it recursively, we're going to send over the address of node B. So now, when we come to this method recursively, let me erase this. This here is going to be our new P. So this is a new recursive call, and P is now pointing to this node right here. And what are we going to do? We're going to print that node. The first line of code says print it right here. We print that node, so we print the B. And then we recursively call it to the left. So now we're going to call it to the left, and we can see here, there's nothing over here to the left. Then we recursively call it to the right. There's nothing over here to the right. So we printed, then we went left, and we went right at node B. And now node B is actually finished. And so I want to actually back all the way up. And I want to really look at this more at a holistic level. And what do we really have here? We really have three instructions. Those three instructions are print, go left, go right. Those are the three instructions. Print, go left, and go right. And so when we initially call, let me go and write the output right here again. And when we initially call this particular method on node A, well, node A has 3 instructions. What are the 3 instructions? Print, go left, go right. So when we print A, we print it. Well, here's A. And now we go left. Well, when we come left, now we're going to be right here. And this is our P, pointing to this node, node B. Well, what are the 3 instructions of node B? Print, go left, and go right. So we print the node that we're pointing to, we print the B, and so that's done. And now we go left. Well, when we go left, we see there's nothing here. And then we go right, we come right, there's nothing here. And so now we've done all 3 instructions of that particular recursive call for node B. We've done all 3 instructions. And so now this particular instruction here, what was that instruction that I just circled? That was go left on A. Well, we just went left on A. We did all 3 of those instructions. And so now this instruction of going left on A, it's finished. So we can close all of that out. We went left on A. And so now we need to go right from A. And we come right to right here. We're at C. And C has 3 instructions. What are those 3 instructions? Go left, print, then go left, then go right. Well, we print C. So we're done with that. We then go left on C. So we come here and we go left. There's nothing. Then we go right. There's nothing. And so C, we've done all 3 instructions of node C. C finishes. We've done all 3 instructions. And we're back at node A. And in fact, we've done all 3 instructions for node A, and the method is complete. So this is the idea of pre-order and using that particular code. So here, what do we do here? We print node A. We then go left, and we come to node B. Well, node B has 3 instructions, which is print, left, right. Well, from node B, we print B. We then go left. There's nothing there. We then go right. Nothing there. Well, B is now finished. So then we come back to A, and A has 1 more instruction. Remember, what were the 3 instructions for A? Print, left, right. So we printed A. We went left on A. It brought us to B. We did all of B. So now we're done with that instruction left of A. And now we're at the instruction called go right on A. Well, when we go right on A, we come to C. Well, C has 3 instructions. Print left, right. We print the C. We then go left. We then go right. Let's do another one. Here is a larger one, and I'm going to come back over to the tablet. And let's solve this one here at the tablet. So we have here, how many nodes are this? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 nodes. And we want to do pre-order traversal. I'm going to tell you, I think the easy way of doing this is I'm going to come over here and I'm going to write ELR, which is print left, right. I'm going to write that next to every single node so I don't lose track of what I'm doing. Because ultimately, when I do the recursion, each one of these nodes has to execute those 3 instructions. Print left, right. I don't really even need to do the last level, but I'll write it, no problem. Print left, right. Print left, right. And we have one more, print left, right. So let's go through this and let's see how easy it is when you actually do it in this process. We start at the root. What is the first instruction of A? Print it. So we print A. And then what do? Just look at what's next. We go left. Well, when we go left, we come here to B. And so now we're at B. What is B's first instruction? Print it. So we print B. What's B's second instruction? Go left. And so I'm going to scratch out that instruction. I come left to B. I'm at D. What is D's first instruction? I print it. So I print the D. Now pay attention here. Because I'm scratching off all of these things, right? I can see exactly where I'm at in my instructions. I just printed D. Now I have to go left at D. And when I go left, I come to G and I print G. And after printing G, I need to go left on G. There's nothing. Then I go right on G. There's nothing. Well, guess what? I can see that all of G's instructions are finished. Now I go back up to where I came from, which was D. I'm at D, and D's next instruction is go right. So I go right from D. I'm now at H. I print H. I then go left from H, nothing. I then go right on H, nothing. And you might say, well, where do I go now? Well, the value of all of this is pretty clear, is I finished that. So I go back up to how I got from there, and I've finished all of that. So then I come back up to there, and now I'm back at B. What did I already do on B? I printed, I went left, now I go right on B. So it brings me to right here. I'm at E, I need to print E. I then go left on E, there's nothing. I then go right, I come to I print I. I then go left, there's nothing. I go right, there's nothing. I has now finished. So I go back to how I got to I from E. E has finished. So how did I get to E? I came there from B. I go back to B. Well, B has finished. So now I go back to how I got to B, which is from A, and I'm back at A. And what's next? Well, you can see we never went right yet. So I go right. I come down over here to C. And C has 3 instructions. I need to print C. After I print C, I need to go left. So I come here to F. I print F. That's the first instruction of F. We print F. We then go left. There's nothing to the left. We then go right. So we come this way. We're at J. We print the J. We go left of J. We go right of J. And what's next? I will tell you we've printed everything, but if I were to ask you right now, it's a great question. After going right on J, although there's nothing left to print, what instruction is actually left that we need to execute? And just back up. You say, well, if J is done, we come back to where we were, to F. We've already printed left and gone right on F, so F is done. So go back to what brought us to F, which we came to F by way of C, and we realize, oh yeah, we still got one more instruction that's going right on C, right? Going this way, and there's nothing to the right of C. And so that is a detailed example of doing a pre-order traversal on a tree with here 10 nodes. Not that bad. I'm going to skip through all of these since we just did that live on the tablet. Let's now look at an in-order traversal. An in-order traversal is the route is visited between the left and the right subtrees. So here, when we visit, of course, we're still printing again, but now instead of printing, then going left and right, we're actually going to go left, then we're going to print, and then we're going to go right. So that's all that changes. So instead of print, then left, right, notice we have left, then we print, and then we go right. Let's look at this example. We have 3 lines of code for every node. Go left, then print, then go right. So here, when we're at node A, right at the beginning, we need to go left, and we come to B. Then we need to go left again. There's nothing to the left. Then we're at B, and now we actually print node B, and then we go right. So once again, this is actually easiest and best explained on a tablet. Let's head over. Here we have that exact code with this tree. So at the beginning, once again, P is pointing here to A. This is P. It's pointing over. Click here. That's our P, and it's pointing over to A. Now, there are 3 instructions for A. What are those 3 instructions? The 3 instructions are go left, then print, and then go right. Those are the 3 instructions. And in fact, I say those are the 3 instructions for A, but once we go left on A and we arrive at B, well, B will have 3 instructions because B, right here, will be the new P referred to. And B will have 3 instructions, which are left, then print, then go right. So here, the first 3 instructions are left, print, and right. And so just like we did on that last example, I'm going to write down LPR, left, print, right, left, print, right, left, print, right. I'm going to write that down next to every single node. So at the beginning, we're at node A. What does it say? It says go left. So we go left. We arrive at node B. What is B's first instruction? Go left. We do so. There's nothing there. What is B's second instruction? Print. So now we print the very first value. We print node B. We print B. Now B's third instruction is go right. We go right. There's nothing there. So we're done. We can see we've done all 3 of B's instructions. So now we need to go back. This particular recursive call is popped off of that recursive stack. And now we go back to whatever instruction called us. Well, how did we get to this particular node or this method call? We got there by way of A, right? A called A left, and that's how we got there. So now that we finished this, we're going to actually go back and we're going to do A's next instruction. What is A's next instruction? Print. We print A, and then we do A's third instruction, which is to go right, and we come to node C. Node C's first instruction is go left. We do that. There's nothing there. Then we do C's second instruction, which is to print C, and then we do C's third instruction, which is to go right, and there's nothing there. This is how we do an in-order traversal. So we printed B. After printing B, we print A, we then print C. Let's once again see a longer example of this. So we head over to the tablet. We already have this set up for us, left print right, written next to every node to make it easy. And let's run through this. So A's first instruction is go left. So we go left, we're at B. B's first instruction is go left, we go left, we're at D. D's first instruction is go left, I cross it out, I come to G. G's first instruction says go left, I go left, there's nothing here. G's second instruction is print. So now I'm going to actually print the G. G's third instruction is go right. I come right, there's nothing here. Guess what? G is now completely done. So now that G's done, we go back up to D and we do D's second instruction, which is print. We print the D. We then do D's third instruction, which is go right. So we're going to come over here. We come to H. H's first instruction is go left. There's nothing there. H's second instruction is print. We print the H. The third instruction is go right. There's nothing there. H has now completely finished. So we go back to how we arrived to H, which is from D. But if you look at D right here, we already went left, we printed, and we went right on D. D is also completely finished. So now we go back to B. And we're at B, and B's second instruction is print. We print B. We then go right, and we come to E. E's first instruction is go left. We go left. There's nothing there. E's second instruction is print. We print E. We then go right, which is the third instruction for E. We go right. We arrive at I. I's first instruction is go left. There's nothing there. I's second instruction is print. We print I. The third instruction is go right. There's nothing there. I finishes. We go back to E. Well, guess what? E has completely finished. So now we go back from how we got to E, which is from B. Well, guess what? B has completely finished. We've already gone left, printed, and gone right. So now, after going back to B, we actually go back to A, and we're finally at A's second instruction, which is to print A. So we print A, and I want to stop here for a moment and just point out, what was A's very first instruction? It was go left. And notice how when we went left on A, we did all of that. A's second instruction is print, and we just printed A right here. And now we're at A's third instruction, which is to go right, and we're finally about to go right and do this and do the right side of A's right subtree. So now we're going to go right, and we come to C. We go left at C, that's the first instruction. We come to F. We go left at F, there's nothing there. We print F. We then, after printing F, go right. And we come to J. We go left from J, that's the first instruction, there's nothing there. J's second instruction is print. We print J. J's third instruction is go right. There's nothing there. J has finished, so we go back to F. F has gone left, printed, and right. We've done all three instructions of F. We then go back to C. C's next instruction is actually to print. We print C. And C's third and final instruction is to go right. That finishes. Once C finishes, we come back to A, and we've already now done all three of A's instructions. And so here, that's now been done live, so I can just click through all of this, and the very last value that got printed is node C. That was in order traversal. Post-order traversal. Now this should feel pretty easy. Post-order is the same concept. It's just the ordering. We're going to print at the very end. We're actually going to go left, then right, and then we're going to print. Here's the code. We go left, we then go right, and then finally we actually print. And so let's apply this on this tree right here, coming over to the tab. We have that code, we go left, we go right, and then we print. So I'm gonna write next to each one of these again, left, right, print, left, right, print, left, right, print. So we're at A. A's first instruction is go left. We come over to B. B's first instruction is go left. There's nothing there. B's second instruction, go right. There's nothing there. B's third and final instruction is print. Now we actually print B. And then we finish B. We come back to A. A's second instruction is go right. So we come over here to C. C's first instruction is go left. Nothing there. C's second instruction, go right. Nothing there. C's third instruction is we print C, and now C has finished. We come back to A, and A's third and final instruction is to print. And so the very last thing that actually gets printed is the root of our actual tree. So here we print B, we print C, we print A, and we have one more large example to go over. I'm gonna head over to the tablet. And here we have left, right, print written next to every node. I did not even write it to the leaf nodes because you're just going to ultimately print it after going left and right. So from A, I go left, B, I go left, D, I go left, I'm at G, I go left, I go right, then I print G, G's done, I come back to D, D, I go right, I come to H, H, I go left, right, print, I print H, H is now done, I come back to D, I finally print D, D's done, I come back to B, I go right on B, brings me to E, E, I go left, there's nothing there, I go right, which brings me to I go left and right, and then I print I finished I go back to E, I print E, notice I'm going faster here, E's done, I come back to B, and now I just print B. And now I go back to A, because B is now done, I go back to A, and finally I go right on A, I go right on A, it brings me to C, I go left on C, which brings me to F, I go left on F, there's nothing there, I go right on F, I come to J, I go left and right, and then I print J, and then I come back to F, because J is done, I print F, I come back to C, since F is done, I go right on C, there's nothing there, I then print C, and I then finish with C, and I come back to A, and we have one final instruction, which was we print the actual root of the tree. So 3 traversals, we've seen all 3 of them in detail, and now what remains is really just practice. I say here, as a final traversal example, feel free to pause the video, don't look at those solutions, trace through it, make sure you understand those traversals, and you get that exact same answer. A bike lock fail picture, this is incredible. This is about 10 years old. I took this one at UCF teaching, and it's a great picture, to be very honest. I mean, come on, you got a post, someone locks their bike to a post. What an incredible bike fail picture. You know, people are tired, life happens. When you delete a block of code that you thought was useless, and you're just, yeah, we've all done that, unfortunately. All right, so what we're going to end with is 2 more things. We want to cover breadth first traversals, and we want to also introduce this idea of binary search trees. So a breadth first traversal, as opposed to the depth first traversal where we go all the way deep down as far as we can go until we get to some leaf node, and then we backtrack and we go down a different path, a breadth first, we go as wide as possible. We're effectively going level by level. So here, if I just click ahead, we can see on this sample, this is more of a bird's eye view of what is a breadth first traversal. We're really going to end up going level by level, and we're going to visit node J before we ultimately visit node N. This is the overall idea of a breadth first traversal. So now in particular, check out how easy this is. Given this particular tree, and we can see here it's a complete binary tree because every level is filled completely and every node has 2 children nodes or no more than 2, so it's a binary tree. Check out what would be a breadth first traversal. It's literally H, then DL, then BFJN, and then ACEGIKMO. That's it. That is the breadth first traversal. Literally, you go level by level from left to right. One of the easiest questions you can possibly answer. What you want to focus on, however, is how would you code that up? What would you do to code that up? Think about how we just coded those three depth first traversals, right? We used recursion. It was a small method. We said as long as P does not equal to null, we said we'll print, then we go left and right. or we'll go left, then we print, then we go right, or we go left and right, then we print, right? Correct? So here, how would you actually accomplish this traversal? Imagine we have access to the root of a tree. How would you print that root and then go level by level, printing all of the values or traversing through this entire tree in a breadth first fashion, level by level from left to right? Pause the video, spend 5, maybe if you want 10 minutes, think about how you would possibly do that in code. And I'll tell you, it's a solution that most would not think of because it's very unique and I would say super cool. Of course, I'm a nerd. So if you want to traverse and print all of those nodes, what we're going to use is an actual queue. We're going to enqueue the root node into the queue, and now we have a while loop. While the queue is not empty, what do? We dequeue the node, that is of course at the front of the queue. We print this node, and then we enqueue its children, the left child and then the right child, and that is it. So let's head over to the tablet to actually see how we can do this one. Here we have the tree, we have our output that I'm going to put up here, and we have our queue. So step 1, it said enqueue the root. Done. So now we have a while loop. The while loop says while the queue is not empty, dequeue, I'm going to scratch it off. It said step 1 is dequeue, step 2 is print that node you dequeue, and then enqueue the children of H, which are what? D and L. So we're going to enqueue D and we're going to enqueue L. Now continue. Dequeue, which is the D, print the D, and then enqueue its children, which are B and F. So enqueue B and F. Continue. While the queue is not empty, dequeue the L, print the L, and then enqueue L's children, which are J and N. So we're going to enqueue J and N. Continue. The queue is not empty, dequeue, print, and then enqueue the children of B, which are A and C. Done. Continue. Dequeue, we dequeue F, we print F, and then we enqueue F's children, which are E and G. And then we continue, dequeue, print the J, and then enqueue J's children, which are I and K. And then we continue, dequeue the N, print the N, and then enqueue N's children, which are M and O. Let's do one more. Now you would dequeue the A, you print the A, and you would enqueue A's children, and you see here that A has no children. And so if you really look what's left, we have C, E, G, I, K, M, O, and that's exactly what we have left in our queue. So really, really cool that how we actually print or traverse a breadth first traversal of a tree is by using another data structure. How cool, I say here on the next slide, kind of nerdy and really cool that we're using one data structure to traverse and then print out the contents of another data structure, a tree. This is actually a braining moment, kind of cool. Last thing, this idea of binary search trees. So we've seen how to traverse binary search trees. It's incredible. This is a 40-minute video here. And we've talked about traversing of trees. We've talked about all kinds of tree terminologies, a full tree, a complete tree, the height of a tree, all kinds of tree goodies. And everyone's with me like, yeah, I got this. I know how to traverse a tree. Okay, what's the purpose? Like really, I haven't even talked about that yet. What is the purpose of this data structure? What is the value of this data structure? Here's the answer. The value of this data structure comes when we add this restriction. Consider this tree that you see here. What kind of pattern can we identify? What can you see? Pause the video and try to identify the organization that is occurring of those nodes. Just pause the video, spend 30 seconds, and ask yourself, in what manner are those nodes being organized? And what we can see is for every single node, all of the nodes stored to the left of that node are smaller than that node, and all of the nodes that are stored to the right of that node are larger, are greater than that node. So pick any one of these nodes. Pick this node 8, the root. Everything to the left of 8 is smaller, including this 7, because that's to the left of 8. And now look to the right of the 8. Everything to the right is larger. Pick any other node. Pick the 6. Everything to the left of the 6 is smaller than the 6. Everything to the right of the 6 is larger. And confirm that for any other node. Why would this be a desirable property? And the answer is simple, because now searching for a node is super fast. How many nodes do we have here? We have 1, 2, 3, 4, 5. We have 9 nodes. Imagine if we were looking for node 14 in a list. We would just traverse from beginning to end. It would be an O of N traversal. But now check this out. If I'm looking for the node 14, I'm going to start at the root. I'm going to say, hey, root, are you 14? Root says, no, I'm not 14. Cool. Is 14 smaller than you? No. Oh, cool. So it must be bigger. So now we're only going to look at this right side for 14. And we come to 10. Hey, 10, are you 14? No. Is 14 smaller than you? No, it's bigger. Cool. So we go to the right of 10 and we say, hey, are you 14? Yes, I'm 14. Well, check that out. Now searching for a node is super fast. It would normally be O of N time, but this ordering property, where smaller nodes are to the left of a given node and any nodes that are larger go on the right side, what we're effectively doing is we are having the search space, which smells like O of log N, right? If this tree were completely balanced and were a complete tree, we can guarantee that searching for a node would actually be log N. So all of the data values in the left subtree are going to be smaller than the data values of the root. And all of the data values in the right subtree are going to be larger than the data value of the root. And both the left and the right trees of a given node are of course, going to be binary search trees. So let's check out this one right here. What if I'm looking for the 28? I'll start here at the 44. Are you 28? No. Is 28 smaller? Yeah, I come to the right here. Are you 28? No. Is 28 smaller? No, it's not. Okay, so I'm gonna come to the right. Are you 28? No. 36 is like, I'm not 28. Cool. Is 28 smaller? Yes, it is. We come here. Are you 28? Perfect. We found 28. Check out how quick that is. Let's actually look for one more that's not even in this tree. How about 57? Are you 57, 44? No. Is 57 smaller? No. Go right. Are you 57? No, I'm not. Is 57 smaller? Yes, it is. Go left. Are you 57? No. Is it smaller? No. Okay, so go right. 62, are you 57? No. Is 57 smaller? Yes, it is. Go left. 58, are you 57? No. Is it smaller? Yes, it is. Go left. We've arrived now at an empty position. It's null, so therefore we can say it's not found. This is now super, super quick. So a binary search tree, often called just a BST, is extremely useful for searching. What we've done, which is super cool, we have effectively embedded the idea of binary search into now a linked dynamic data structure. This is incredible, right? We talked about the advantages and the disadvantages of these different data structures. The advantage of a linked list over an array is what? That we now have it's dynamic. It's not a fixed size. We avoided shifting. What's the negative of a linked list? Traversing is trash. We no longer have direct access. We can't immediately access and find those nodes. Now everything's O of N to be able to go traverse through and find the node we're looking for. But when you're talking about now and we've lost binary search as well on an array, which is super fast to search through a sorted structure, log in. Well, now with a binary search tree, we get almost the best of both worlds. We don't have direct access, but log is pretty fast, right? So given a tree of 1 billion nodes, we can find our node within log of n, within 30 searches, with the condition that the tree is balanced, and we're going to talk more about that. So super cool that we've effectively embedded this binary search, this super fast search, into a dynamic linked data structure. What remains is we need to learn more about binary search. How do we insert into the tree? It follows these rules. Smaller items go to the left, bigger items go to the right. How do we delete from this binary search tree? How do we delete items, and how do we maybe reorder this tree upon a deletion? More rules are involved in that. We're going to cover it. Video's been too long. As always, it's been fun. Historic? I don't know about historic. Our despair.com demotivator, doubt in the battle, ouch, between you and the world, bet on the world. I would say bet on yourself. I'm in a positive mindset right now. Take care, everyone. It's been fun.